Hello, everybody, and welcome to a new week and a new video. In the past couple weeks, we determined the measures of central tendency, which describe the typical data value. And then we discussed measures of dispersion, which describe the amount of spread in a set of data. And this week, we are going to discuss measures of position, which describe the relative position of a certain data value within the entire set of data. Our goal for this week is to determine and interpret Z-scores, interpret percentiles, determine and interpret quartiles, determine and interpret the interquartile range, and then check a set of data for outliers. So let's consider this example to understand why do we need the Z-scores. Let's say that at the end of 2010 season, the New York Yankees led the American League with 859 runs scored, while the Cincinnati Reds led the National League with 790 runs scored. It appears that the Yankees are the better run producing team. However, this comparison is unfair because the two teams play in different leagues. The Yankees play in the American League where the designated hitter bat for the pitcher, whereas the Reds play in the National League where the pitcher must bat. Pitchers are typically poor hitters. To compare the two teams scoring for runs, we need to determine their relative standing in their respective league. We can do this using the Z-scores. So what are those Z-scores? The Z-score represents the distance that a data value is from the mean in terms of the number of the standard deviations. We find it by subtracting the mean from the data value, and then we divide that value by the standard deviation. For the population Z-score, we use mu and we use sigma. And for the sample Z-score, we use X bar and we use S. If a data value is larger than the mean, that means the Z-score is positive. And if the data value is smaller than the mean, then the Z-score is negative. If the data value equals to the mean, that means the Z-score is going to be 0. A Z-score measures the number of standard deviations an observation is above or below the mean. For example, a Z-score of 1.24 means that the data value is 1.24 standard deviations above the mean, and a score of negative 2.31 means the data value is 2.31 standard deviations below the mean. Let's consider this example to further understand the using of Z-scores. This example says the mean height of males 20 years or older is 69.1 inches with a standard deviation of 2.8 inches. The mean height of females 20 years or older is 63.7 inches with a standard deviation of 2.7 inches. Data is based on information obtained from the National Health and Examination Survey. Who is relatively taller? Kevin Gray, whose height is 83 inches, or Cadence Parker, whose height is 76 inches. So to compare those two people, we cannot say that Kevin Gray is taller because Kevin Gray belongs to the males group and Cadence Parker belongs to a different group, the female group. So we're going to calculate the Z-score to be able to compare the two heights. So next, we're going to calculate the Z-score for Kevin. For Kevin Gray, the Z-score is his height is 83 inches minus the mean, which is 69.1 inches, divided by the standard deviations for the males, which is 2.8. The answer is 4.96. And we calculate the Z-score for Cadence Parker. Her height is 76 minus the mean for the girls, which is 63.7. And then we divide that by the standard deviations for the women or the females, which is 2.7. The answer is going to be 4.56. So let's compare the two and understand what those means. The first Z-score for Kevin Gray means that Kevin Gray's height is 4.96 standard deviations above the mean because it is positive, while Cadence Parker's height is only 4.56 standard deviations above the mean. That means Kevin is relatively taller than Cadence. Next, we will interpret the meaning of percentiles. Recall that the median divides the lower 50% of the set of data from the upper 50% of the data. The median is just a special case of a general concept called the percentile, or later we're going to refer to it as a quartile. So what is the percentile? The kth percentile, and we're going to use the notation P sub k of a set of data, is a value such that k% of the observations are less than or equal to the value. So percentiles divide a set of data that is written in ascending order into 100 parts. Thus, 99 percentile can be determined. For example, P sub 1 divides the bottom 1% of the observations from the top 99%, and P2 divides the bottom 2% of the observations from the top 98, and so on. And that is displayed in the graph right here. Percentiles are used to give the relative standing of an observation. Many standardized exams, such as the SAT college entrance exam, use percentiles to let students know how they scored on the exam in relation to all other students who took the exam. Now let's look at this example to interpret percentiles. The Graduate Record Examination, GRE, is a test required for admission to many U.S. graduate schools. The University of Pittsburgh Graduate School of Public Health requires a GRE score no less than 70th percentile for admission into their Human Genetics MPH or MS program. We want to interpret this admission requirement. So what that means in general, the 70th percentile is the score such that 70% of the individuals who took the exam scored worse and 30% of the individuals scored better. In order to be admitted to this program, an applicant must have a score as high or higher than 70% of the people who took the GRE exam. And put in another way, the individual score must be in the top 30%. The most common percentiles are quartiles. Quartiles divide data sets into fourths, or four equal parts. The first quartile, denoted Q sub 1, divides the bottom 25% of the data from the top 75%. Therefore, the first quartile is equivalent to the 25th percentile. The second quartile, denoted Q sub 2, divides the bottom 50% of the data from the top 50%. It is equivalent to the median, or we could say it is equivalent to the 50th percentile. Finally, the third quartile, which denoted Q sub 3, divides the bottom 75% from the top 25%, and it is equivalent to the 75th percentile. This figure shows you the three quartiles. So by hand, how are we going to determine the quartiles? To find the quartiles, we first need to arrange the data in an ascending order, much like when we find the median. And then we're going to determine the median of the data, which is equivalent to the second quartile. The median is going to divide the set of data into halves. The observations below the median, or to the left, and the observations above the median, or to the right. The first quartile, Q1, is the median of the bottom half, and the third quartile is the median of the top half. Let's look at this example to determine and interpret quartiles. A group of Brigham Young University, Idaho students, Matthew Herring, Nathan Spencer, Mark Walker, and Mark Steiner, collected data on the speed of vehicles traveling through a construction zone on a state highway, where the posted speed was 25 miles per hour. The recorded speeds of 14 randomly selected vehicles is given below. That is 20, 24, 27, 28, 29, 30, 32, 33, 34, 36, 38, 39, 40, 40. And we want to find and interpret the quartiles for speed in the construction zone. So first we're going to do that by hand, and then I will show you how to do that using Excel. We will have different answers, but they are very close to one another, so we're not going to care that much about the results. First step is to arrange the data in an ascending order, and as you noticed, our data is already in an ascending order, so we don't need to do that step. Now we determine the number of observations, which is 14 observations. So the median is going to be the mean of the 7th and 8th observations, and that value is going to be 32.5, which is the same as the second quartile. And then the median of the bottom half of the bottom half of the data is 20, 24, 27, 28, 29, 30, and 32. We calculate the median for this set of data, and the median is going to be 28. Therefore, the first quartile is going to be 28. If we're going to use Excel, we will end up with 28.25. The median of the top half of the data is the third quartile, or Q3. Therefore, Q3 is going to be 38. With Excel, it's going to be 37.5, which is not a big deal. So how do we interpret those quartiles? And here is the interpretation of those quartiles. 25% of the speeds are less than or equal to the first quartile, 28.25 if using Excel, miles per hour, and 75 of the speeds are greater than 28 miles per hour. 50% of the speeds are less than or equal to the second quartile, which is the median, to 32.5 miles per hour, and 50% of the speed are greater than 32.5 miles per hour. 75 of the speeds are less than or equal to the third quartile, 38 miles per hour, and 25% of the speeds are greater than 38 miles per hour. Next, we're going to determine and interpret the interquartile range. The interquartile range, we denoted IQR, is the range of the middle 50% of the observations in a data set. That is, the interquartile range is the difference between the third and first quartiles and is found using the formula IQR is equal to Q3 minus Q1. So looking back at the previous example, we can calculate the interquartile range of the speed data. We know that Q1 is 28 and Q3 is 38. So the interquartile range is going to be 38 minus 28, that is 10. Or using Excel, it is going to be 9.25. The range of the middle 50% of the data speed of cars traveling through the construction zone is 10 miles per hour, or we could say it is 9.25 miles per hour with Excel. This interpretation of the interquartile range is similar to that of the range in standard deviations. That is, the more spread a set of data has, the higher the interquartile range will be. Suppose that a 15th car travels through the construction zone at 100 miles per hour. How much does this value impact the mean, median, standard deviation, and interquartile range? After the calculations, we find out that without the 15th car, the mean is going to be 32.1 miles per hour, while with the 15th car, the mean is going to be 36.7 miles per hour. As we discussed before, the mean is not resistant, so you see a dramatic change in the mean, while the median did not change that much because the median is resistant. Now let's compare the standard deviations and the interquartile range. As you can see, the standard deviation was affected dramatically by that extreme value that we added to our data, while the interquartile range was not affected that much. And therefore, when the distribution of data is highly skewed or contains extreme observations, it is best to use the interquartile range as the measure of dispersion because it is resistant. So that means if the shape of our distribution was symmetric, then we're going to use the mean as a measure of central tendency, and we're going to use the standard deviation as a measure of dispersion. If the shape of our distribution was skewed left or skewed right, we're going to use the median as a measure of central tendency, and we're going to use the interquartile range as a measure of dispersion. When performing any type of data analysis, we should always check for extreme observations in the data set. Extreme observations are referred to as outliers. Outliers in a data set should be investigated. They can occur by chance because of error in the measurement of a variable during a data entry or from errors in sampling. So how are we going to check for those outliers in our data? To check for outliers by using quartiles, first we need to determine the first and third quartiles of the data, and then compute the interquartile range, and then determine the fences. Fences serve as cutoff points for determining outliers. So the lower fence is going to be the first quartile minus 1.5 times the interquartile range, and the upper fence is going to be Q3 plus 1.5 times the interquartile range. Basically, any data that is below the lower fence or above the upper fence is considered an outlier. So using the same example that we used before with the speeding data, let's check the speed data for outliers. First, we're going to find the first quartile and the third quartile, and we found those already, 28 or 28.25 and 38 or 37.5 miles per hour. Next, we're going to determine the interquartile range. It is 10 miles per hour or 9.25 miles per hour. The fences are going to be, the lower fence is going to be Q1 minus 1.5 times interquartile range, which is equivalent to 28 minus 1.5 times 10, that is 13 miles per hour. The upper fence is going to be Q3 plus 1.5 times the interquartile range, which is 38 plus 1.5 times 10, that is 53 miles per hour. There are no values that are less than 13 miles per hour or greater than 53 miles per hour. Therefore, there are no outliers in our data.